Okay, so this is a new section of volume, and in this lesson we're talking about two graphs forming a solid. In other words, when there's a gap or a hole, oftentimes this is called the washer's technique. So basically, the donut or washer shape that I'm talking about arises when a region bounded by two curves is revolved about a line. And so you actually don't see the actual three-dimensional surfaces in a donut or a washer, but when you slice it up into small parts, you see donuts or washers. This lesson outlines the procedures for evaluating donut volume, um, only symmetric about one of the axes. That's what we're talking about here, and we'll actually get into when it's not symmetric about the axis, when you're actually revolving regions about lines, like a random line that's not one of the axes, like maybe y equals 2 or something, and that's a later video. Probably the next lesson, actually, but some video off in the future. And this video also, not this video. This video is only introductory to this whole new idea of volume. But in the next videos, I'll have some example problems. But let's take a look at, well, first, before we do any of that, what I want to let you know is the formula for finding the volume of using this donut washer idea. That is the formula. You've probably never seen it before, but I just thought I'd point this out first. I'm joking. You have seen this before. This is the same formula, actually, for when we were just talking about disks. It's the same exact formula. Nothing changes. So why do we need to have a whole new lesson? Why do we need to have a whole introductory video just about donuts or washers if it's the exact same? If we use the exact same formulas as disks, because it's a new concept and the radius is going to be something crazy. Not that crazy, but it's going to require you to start thinking a little bit differently. The radius is not simply just going to be one function in this case, because there are now two functions we're dealing with. First things first, people call this the washer method because, well, when you split up a three-dimensional surface, like over here in the top right corner, I drew a three-dimensional surface which probably looks like nothing you've ever seen before. But yeah, it's as they say, drawing three-dimensional surfaces is pretty difficult. That's why in your textbook, oftentimes they'll have like computer-drawn things, which is a lot better than anything I could ever draw or your teacher could ever draw or anything. But just imagine that it's partly sticking out from your screen. It's partly sticking out towards you and partly sticking out away from you. So there's some of it's in the foreground, some of it's in the background, actually. But like you could think of this as like the head of a dragon or anything that has a mouth, any organism that has a mouth. This is the mouth, actually. This is the right above the mouth. This is right below the mouth. And you want to find the volume of this thing. Let's say you're asked to find the volume of this thing. Now you don't want to find different color. You do not want to find the volume of this section. You don't want to find the volume of the actual mouth. The mouth is hollow. There's nothing in the mouth. You could care less about that. What you want to find the volume of is all of this. And so calculus, though, what you do with calculus, of course, is you come up with the radius, which might be like your radius might be that, whatever. You come up with the radius, and then you have an infinitely small width for the you split up the volume into lots of different sections with infinitely small width. So the width is just dx or dy or whatever, in this case dx. And then you add up those really small, infinitesimally small sections. You add them all up on an interval, which is the different limits of the integral, which you might have from there to there or something. So that would be like a, and that would be like b, right? That's how you would do it in calculus. So in order to evaluate an integral in calculus, but evaluating an integral in calculus, but you don't want to include this. So to take out the middle part, that's kind of a pain, and it's not easily done. You can't just easily ignore the blue part but find the volume of everything else. Because your radius cuts through the blue part. The purple line is cutting through the blue part. So you have to split up your radius so that it doesn't cover the blue part. Anyway, which this all makes more sense when you actually split up the volume into little small parts, which when you do that, you end up with shapes that look like this. Hence the washer name, or the donut name. I think washer is a little more common of a term to refer to this, but I like the word donut better. I just like the word donut better. But logically, if you think about just one of these small things that it comes when you split up your surface, the volume of this, or area of this donut here, is equal to the area of the whole thing. So the whole thing, the whole circle here, the big circle, the one I'm drawing a red line about, equals the area of that circle minus the area of this circle, the small circle. So the area of the donut, meaning by donut, I mean, obviously I'm not including the inside hole because there's nothing in the hole, right? So this is my frosting on my donut. So the area of the donut is equal to the area of the big circle, okay, minus the area of the small circle. That should actually make sense because you're taking a huge area of the whole big circle, and then you're just taking out the small area, so you're just left with everything outside the small, because you just have everything in here. And so, that's an easy technique to use for finding volume. So basically, you can use the same idea that you would use for volume of a surface with disks without any hollow points or anything. It's the same technique idea, except the radius now, you have a different way of finding the radius. The radius is different because before, when there wasn't a hollow point, if you just had one standard circle like that, your radius just went, that was your radius. Now your radius isn't that, of course, because you don't want any of this hollow stuff in there. So your radius is, well, what you're going to do is you're going to have your big radius minus the inner radius. So you have that radius, and then you're also going to have like if I were to, hold on, let me copy my donut. So if I were to, are you serious? Wow. Sorry, the tool doesn't like me. But when I copy, when in order to find my my new, here we go. In order to find my new radius, I'm going to take the big radius here, and then I'm going to subtract it from the inner radius there. So you have your big radius, which you could call like r sub 1, and then you have your small radius, which you could call r sub 2. And so your full radius, the radius of, as it relates to the actual donut part with the pink frosting, is just r sub 1 minus r sub 2. And so this works really well. And so when we were using our formulas to find volume with washers, basically we're only going to rely on r sub 1 and r sub 2, which are the two radiuses of our two respective functions. So r sub 1 is just your f of x. You have like an f of x, that'll be like r sub 1. Then r sub 2 will have a g of x. And so it'll be as simple as that. And so when we're finding the radius for our volumes, now that we're using washer technique, for some of these at least, we're gonna have a difference of two functions because our radius is a little more complex because it's this donut shape, it's this washer shape. So there you go. The radius now involves two functions, and that's really the only way this washer technique differs from the the disk technique that I taught earlier. And so we'll have this problem: y equals x, y equals square root of x equals 0, x equals 1, revolved around the x-axis. That region revolved around the x-axis, which then will include a hollow point. We'll have this problem. I'll explain how to do it in the next video. There you go.